Yo, what's up, guys? Welcome to another video, and this is actually my second recording of this because I forgot to turn on my microphone. Wow, I'm so smart. But basically, today we're going to be entering into the world of basic calculus and introduce the concept of limits. And so, what limits are is essentially a way to describe what is happening at a point of a specific function. And so, essentially, the limit is just a number, and we write it down like this in this notation. We write it down as a limit of x approaches c, some type of number. Let's make this low wide, no, less wide. X approaches c of f of x equal to L. And so essentially what this basically means is that, as we can see here, as the limit x approaches c of the function f of x, it will give us some sort of, some sort of numerical answer. And so what would that look like, visually pleasing? Because I know notation is very hard to understand. So let's say you had the function 2x. So this is the function 2x, right? So from here, we can just write down our equations. And as we can see here, we see that as x approaches 2, from both the left and the right side of f of x, which is just 2x, we can see that the value of y approaches to 4. And so that's just, a basic way of visualizing limits. And so you might be wondering about another limit. This time, let's have the same limit, but this time we're going to put a hole. And if you don't remember what the hole is from pre-calculus, then it is just an area where there is no y value, I believe. It is just emptiness there. It's depression, basically. On the real note, though, that value of y doesn't exist because it's a hole. It just skips over. And here is a big differentiation that I want y'all to realize. We can see here that as the limit x approaches 2 of f of x of 2x is equal to 4. And you might be like, well, f of 2 of 2x is also equal to 4. So therefore limits and f of x, functions like definite functions are the same thing. No, they're not the same thing. Do not think that. Please do not think that. That is wrong. Do not think that. Here's why. I'm going to show it to you. So as you can tell, as a refresher from pre-calc, a hole is essentially where f of x at that point does not exist. So we can see here that this is the same function 2x. We can safely assume that f of 2 of 2x is equal to does not exist because there's a hole. There's a hole there. Like you cannot make a value up because it just skips over it. But since we're talking about limits, we can safely assume that as limit x approaches 2 of f of x, and f of x being 2x, we can say that the limit is 4. And why is that? Well, it's simply because that f of 2 and limit as x approaches 2 are very, very different things. F of 2 is directly at that point. So I'm going to put here directly. And limit as x approaches 2 is just talking about what's happening around that point. It might be very, 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 very close, but it's always approaching. That's what we say as limit x is approaching. We don't say that it's there. We say that it's approaching. That's very, very different. So therefore, we can write this down. As the limit x approaches c in some type of number for f of x, it is not equal to f of c of that number, of whatever number that might be. Make sense? Let's go. So now you might be wondering, well, in this example, we were able to find the limit visually. And if you're good at pattern recognizing or just seeing the picture, you might be like, well, if we wanted to be fancy, we could just put, the limit x approaches 2 of 2x. And then, from here, just put the number in. And then we'll get the same answer, right? And you'll be right about that. So let's go into some examples, shall we? Where we do it algebraically and put the number in. So let's say you had limit as x approaches 4 of some type of function. So let's just say f of x is equal to 1 over x. So from here, we'll just say that limit as x approaches 4 of f of x. And then from here, we can actually just put the value in and replace it for x. So from here, we just get 1 over 4. And that might be your limit in simple terms, and it's very, very simple. This was a very, very simple function to do. But in some ways, you might not get very, very, very simple functions. So let's dive into those, shall we? Let's say you had the limit as x approaches 1, and the function f of x is equal to x squared minus 1 over x minus 1. And once we put everything in, once we plug the values in, we can see that 1 minus 1 over 1 minus 1 is equal to 0 over 0. So from here, if it equals 0 over 0, do not put equal sign on it. I just did that. Don't do that. Say, do as I say, not as I do. So essentially, 0 over 0 just means that it's impossible to get that. Like, don't do that. Like, don't keep it as that. You can't simplify and say this is 1. You can't do that. That's mathematically impossible. But I'll give you 5 seconds to pause the video and see what we're able to do in order to get a actual numerical answer that is not 0 over 0. I'll give you about 3, 2, 1, and let's go. So you might remember this from your calc class, from your I'm sorry, from your pre-calc or algebra class. But if you're able to see correctly, you can see that we're able to factor x squared minus 1. And you might be wondering, well, how can I do that? Well, you can just factor it by x minus 1, x plus 1, because there's a difference of squares. As we can see here, we have a whole, and we can just cancel out the x minus 1. So from here, you're just left with x as approaches 1 of x plus 1. And from here, you can just replace the 1 with the x. I'm sorry, replace the x with the 1, and then you just get 2 as your answer. And so that's a very, very different way of seeing a limit, of seeing, what you can do with it. And now we're going to get into some properties. So I'll write it down above here. So the first property is that the limit as x approaches c of some constant is always going to be that constant. Why is that? Well, let's say you had the constant of 2. This is 2. Y equals 2. We can see that no matter what, from the left or the right side, that the y value is always going to be 2. So that will be a property. Second, the limit as x approaches c, and let's just say we had z of x and g of x, plus or minus z of x, is always equal to the limit as x approaches c, g of x, plus or minus the limit as x approaches c, z of x. So the reason why that is because you can just separate the two, get the limits, and then actually add up to the numerical answer. And the same actually goes if you just multiply them. So from here, you could just put in the same numbers. And then we have a fourth property where the property of a quotient. And so this is where you have, a function divided by another function. It's just equal to, the limit as x approaches c of that specific function over the limit as x approaches c of another separate function. And so then we have our final property. So our final property is that, let's say you had a limit as x approaches c with some kind of constant multiplying the function. You're just able to take that constant out. You could really just put it in front of the limit sign. You're just able to take that constant out, and then you're just left with that limit as x approaches c of that specific function. And so these are some of the properties that you will learn in calculus. It's very important to learn these properties because they're very simple and, especially in a hard class like AP Calculus or, calculus in college, they are very fundamental, but you will need to remember them for, any FRQ questions, any multiple choice questions, especially on the FRQ. On the FRQ for AB or BC, there's always a question about, adding or subtracting limits of functions and trying to find them from two different graphs. And so here's the big part that I want you to know. Here's a big part. A rule is that limit as x approaches c from the left side, or from, just put a minus sign to make it from the left side, of f of x equal to L has to equal the limit as x approaches c from the right side, or the positive side, of f of x is equal to L. They have to be the same in order to say, well, therefore the limit exists. And so what do I mean by that? Well, let's just say you had a random function like this. And it is at 3. So this is f of x. Well, let's try to find the limits of both of these functions, shall we? So let's just say this is 5, and let's just say this is like 2 or something. So we can see here that as a circle I drew, there's a hole. It might not be obvious because my handwriting is atrocious. Promise you it makes sense. So there's a hole in there. What does that mean? Well, it means that the y value there does not exist, or something like that. It just skips it. But we see here that the dot is filled out here. Therefore, there's no hole there. So therefore, for f of 3, we can safely assume that it is 2. Because if you remember correctly, a function has to pass the vertical line test in order to be a function. You cannot have one x value go for 2 different y's. That's just not possible. But if there's a hole, then that's okay. But here's the tricky part. So let's find the limit of the function as it approaches the left side. And from here we can see that we get 5 because this is the left side. And then we find the limit as x approaches c from the right side, because this is the right side. I'm sorry, I put c, I should have put 3. Of f of x is equal to 2. Through this, you can see it visually and algebraically as well. We can safely assume that the limit as x approaches 3 of a specific function does not exist. Why is that? Well, visually speaking, you can see that both these limits don't end up on the same left or on the right side. and therefore the limit does not exist because the another limit is going to another area, and another limit is going to another specific area. And so you can see that with all my other examples, you can see that they always go to one specific area. You can see how in the function of 2x, you can see how both left and the right limits are going to the same thing as 4. Or if you really want to be fancy, you could also go here to my x plus 1. If you were to draw it out graphically and see where that is, you can see that both limits, just like the linear function I showed you before, as it approaches 1, this will be 2. And so that's kind of like a rule for you to keep in your head. It's basically like one of the other properties, like the sixth little property, secret little property. But you just have to remember that in your head that they don't equal, visually, then the limit as x approaches that specific number of f of x does not exist. And so this is an intro to some limits. Obviously, next time we're going to go over some, more complicated limits where you have to take, more higher math into it. But this has been an intro to limits. I really hope you enjoy, guys. I had to re-record the video because my mic wasn't on, so I'm sorry about that. But the good thing is the video's here. So I hope you enjoyed these limits. If I did something wrong, if I did something incorrect in all these, please correct me in the comments. I'll be happy to take your feedback and do better next time. Thank you for watching, and please like, subscribe. Goodbye.